So once we understood the limitations of a priori algorithm, in today's session we'll be discussing about what is frequent pattern growth algorithm and why we are coming for frequent pattern growth when you are also having a priori. So yeah, as we all know, a priori is an algorithm for frequent pattern mining and generates some frequent item set which focuses on generating frequent item sets and also discovering the most frequent item set. But as we already see, a priori has some drawbacks or limitations that are at each step candidate sets have to be built. So as I said, for every iteration you need to build your item set, and to build the candidate item sets the algorithm has to repeatedly scan the complete database, so that if it is a small database then there will not be any problem with generation of item sets. But if you're talking about some big transactions, then definitely a priori may fail to give appropriate results, and it may take longer time, and also time complexity and space complexity of a priori will be very high. Okay, so these two properties inevitably make the algorithm very slow when compared with the other next algorithms. So to overcome these problems and to overcome these redundant steps, a new association rule mining algorithm was developed, and they named it as frequent pattern growth algorithm. So in today's session, we'll be having a brief understanding of what actually is this frequent pattern. And as we said, FP growth algorithm doesn't need candidate key generation for every step. That is the major advantage of FP growth. Instead, it will be generating a tree based structure that will be useful for evaluating or generating these frequent item sets. Okay, so talking about FP growth algorithm, FP growth is considered as a better or an improvement approach of your a priori method. So if FP growth is generated without the need for candidate generation, as already discussed, FP growth doesn't need any candidate key generation. Instead, it will scan the database and generate a frequent pattern tree. So we need to understand what is a tree structure here. So this tree structure will maintain the association between the various item sets. So as you already studied in the previous years about data structures, so there you have seen about binary tree and all those trees, right, where you traverse your tree from bottom to top and top to bottom. So similarly we use trie data structure here. So for this generation of FP growth FP tree, so you'll be using trie data structure. So yeah, the database is fragmented using one frequent item. So the database is usually used, it will be calculating the support value. And again, for this algorithm also, we will be using support and confidence measures. The only change from a priori to FP growth is, in a priori, we use candidate keys or candidate key generation is done. But in frequent pattern or FP3, we doesn't use candidate key generation. Instead, we go for a frequent pattern tree generation. Okay, that is the big or the vast difference between FP growth and a priori. Okay, so what actually is this FP tree? So because we're constructing it FP tree at the end of this concept, we need to understand how a tree look like and what actually is this tree structure. So I'll first show you a sample tree structure or the result of your FP growth. So this is how you generate your tree. So this can be called as your tree or the output of this sample data set. So I'll explain you about this to the example. So to generate this FP growth tree or FP tree, you need to traverse it step by step, and you need to understand what actually is the root element and what are the branches or the leaves. So you need to remember one important point here. Every time you generate a FP tree, the root node element should always be null. So here you can see the first step or the root is always null. That is the indication that it is a frequent pattern tree. So whenever you are understanding FP tree or writing examinations about FP tree, you need to make sure that FP tree in a FP tree construction, the root element is always equal to null. Okay, that is the first understanding about FP tree. And next, the root node represents null while the lower nodes represents the item sets. So here you can see that branches, some left and right branches indicate the leaf nodes indicates the item sets. Okay, so this is a sample data set what we take to to understand FP growth. Here you can see some 5 transactions, and here you can see some item sets or the what items a person has purchased in each transaction. In first transaction, you can see EKMNOI. So we call this as a monkey problem because those alphabets you can combine to make it as a monkey. So that's the basic way we understand. So for Pagod algorithm, so the monkey data set, they call it as a monkey, or you can see the second one is a donkey. But that is how that is not about this meaning. So these are the actually E indicates one item set, item K indicates one item, M indicates one item. Likewise, each alphabet represents one item in a data set. Okay, so yeah, before going for example, let's make these things clear. So root node indicates null value and the lower nodes represents item sets. Okay, so the association of nodes with the lower nodes, that is the item sets with other item sets, are maintained while forming the tree. So while you're constructing a tree, you need to have a relationship or understanding of how to combine each element or item set, how they are related. That's how we generate an FP tree. Okay, so the output of a priori will be a frequent item sets along with a candidate key generation, but the output of FP tree will be a frequent item sets along with a FP tree. So you need to construct a tree or a traversing method while explaining in your examination. Okay, so these are steps involved in FP growth algorithm. So you will be having some 8 steps, like how you traverse through a tree. Okay, so yeah, in step 1, basically the first step is to scan the database and understand the support values of each item set. So you'll be calculating the support value, and for this algorithm also they'll be mentioning you what is the minimum support threshold value. So that will be very clearly given. So if that is not given, we can assume it by ourselves and we can go ahead. And second step is as part of frequent pattern tree construction, you need to assume that the root element is always is equal to null. That is the second step. And third step starts from the traversing from the data set whatever you are having. Okay, so likewise step 3 to step 5 are nothing, step 8 are nothing but generation of a frequent pattern conditional FP tree. Okay, so I'll again go back to go to your example, and when explaining the example I'll explain each step of the algorithm one by one. Let's first try to understand what is this transaction table. Okay, so the question is construct a FP tree for the below transaction data with minimum support value is equal to 3. So for this data set, they have mentioned clearly that support value is equal to 3. So if it is given as construct a FP tree, we are applying frequent pattern algorithm for this data set. If it is not mentioned as FP tree, then we can apply a priori algorithm also for this data set. Okay, yeah. So the above data set is a hypothetical data set of transactions with each letter representing an item. So here E indicates an item, O indicates an item, and K indicates an item. So the first step is we need to calculate the support value of each item set. That is how many number of times in each transaction an item has been repeated. For example, I start in the ascending order of these elements. So initially I'm taking it in ascending order, or you can calculate support value as your wish also. There is no rule that you need to write support values only in this manner, but it is being done clearly to make you understand in a ascending order. That is item set A has a value of 1. C has a support value of 2. If you want, you can verify it. C is repeated in only 2 transactions, T4 and T5. If I go with D transaction, D is available only in transaction 2. So the support value is 1. If I go with E value, E is available in transaction 1, transaction 2, transaction 3, and transaction 5. So support value is 4. Similarly, for K, the support value is 5. That's how we are calculating here. Frequency is nothing but your support. Here they have termed it as frequency, but we call it as the support value because frequency is nothing but number of times each value repeated in a complete database. Okay, so I hope everybody is clear till this step. So now we move ahead with the next step. That is, after calculating this, as everybody of you said, what are the frequent item sets. Now you can see the values which are meeting the criteria. So we consider it as L. That is uh, the values whichever the criteria is met, they are kept into a separate table called as L. That is K, according to the descending order. Now K value is 5, E is equal to 4, M is equal to 3, O is equal to 3, Y is equal to 3. So these are the values which we take forward for the next steps, because they are meeting the minimum support threshold value. Okay, so a frequent pattern set is built which will contain all elements whose frequency or whose support is greater than or equal to minimum support value. So here frequency indicates support value only. So these elements are stored in descending order of their respective frequencies. So after insertion of these relevant items, the item set K looks something like this. That is L is equal to uh, L here indicates the frequent item set. Okay, yeah. So now we have obtained till this frequent item sets values. Now the next step is, this algorithm is completely different with respect to your a priori. So what we do is we follow, as you can see here, a K is taken first because of the descending order. From top to bottom, we'll be scanning. And now according to this order only, we will be arranging them into an ordered item set. So here in the table, you can see, basically these are the items which we got from the transaction table. But in the next, we have created one more column called as ordered item set. An ordered item set is built according to the values of this support value. So here in the original transaction, you can see in the transaction 1, we are having the values E, K, M, N, O, Y. But in the ordered set, I look into this L data set, and whichever the values are available as per this order, I will then only keep them. Here you can see I'm not keeping E as the first element. I'm keeping K as the first, because as is the ordered item set, it follows some order, that is descending order. So K is kept first, next E, next M, and N is not taken or considered because N is not available in this L subset, because N is not meeting the minimum support threshold value, it is being discarded. In the same manner, for transaction 2, again I will look back to this table and I am eliminating D here, because D is not meeting the minimum support threshold value. Again I will order it in the order of the descending order, that is K, E, O, Y, right? Again K, E, M. I'm eliminating A in transaction 3. In transaction 4, I'm eliminating C and U. And in transaction 5, I'm eliminating C, again I, right? These values are eliminated. So I hope everybody is now cleared about what actually is a ordered item set in this frequent pattern algorithm. Yeah, so moving ahead to the next step here. So now we are going for the tree construction. As I said, we will be constructing a tree based on the item sets or the values which are meeting the minimum support threshold value. So now we will take this L subset of values, the item sets which are having value which is greater than 3, that value is considered. And now we are going for a tree construction. So as I said, the root element should always be is equal to null. Then we will be going with this ordered item set. Now we need to consider this table for tree construction. First, we look into this transaction called as T1. So in T1, I am having the elements as K, E, M, O, Y. So I will be taking these values here. Yeah. So K, E, M, O, Y. I have taken the first transaction values in the formation of a tree, and I have given a value as 1. Why I give the value as 1 here? Because here K is repeating one time, E is repeating one time, M one time, O and Y. Okay. Now this is the first step in creation of your frequent pattern tree. In the next step, I'll look into transaction T2. Now in T2, if I want to construct a T2 tree here, then already I'm having K and E in the first ordered item set. So now let's look at how we'll construct a tree. So now you can look at here, the values are nothing but KEOY. So in the first step, I have mentioned the transaction 1 tree, and in the next step, I will go for the transaction 2. And because the values in transaction 2 are KEOY. So KE, I'm incrementing my count. If you are looking properly, previously the value of K and E are 1. Now because the same values are repeating, I am improving or I am increasing the value of that K is equal to +1 and E is equal to +1. And I am not incrementing the value of O is equal to 2. Why? Because there is a gap here. In between this K, E, O, I am having M in the first transaction, and here I am not having M. So whenever you find a new set of element in the transaction, you need to form a separate branch. Okay, this is very important step in this FP tree construction. So I'm having the values as K, E, O, Y. I have incremented the count of K and E, but because I'm having O as a separate uh, element here for the transaction 2, from E I am traversing it to O and Y, so that when I look in the from bottom to top, it is like E, Y, O, E, K. This is a separate tree. This is a separate tree. Likewise, I'll be getting different branches. For example, if I go for a third transaction, that is KEM. So here you can see only till KEM. So instead of going for a new tree construction, I'll just increment my count for the previous tree. Here the count is 2 to 1. Next, I'll increase the count to 3. That is 2 plus 1, 3. Again 2 plus 1, 3. And for M, I'm having 1, and I'll increase it to 2. I hope everybody is following this. Is it clear till here to everyone what I am doing? So now we look back to the next transaction, that is transaction T4. Now in the T4, I'm looking only into the ordered item set. Forget about these items. Now to construct your tree, we need some ordered item set. That is, I'm looking into now KMY. So up to transaction 3, everything is clear. Now I look for KMY. So now you can compare it with the previous transactions. For transaction T4, after K, I am having M. Up to transaction 3, the value is something like K comma E. But transaction 4, I am having K comma M. So now let's see how a tree will be constructed. So here for K, My, I'm increasing the K value as 4, but I am again going for separate branch here because in between K and M, I am having E. I cannot proceed here, and never increment your count again here. If you are taking a separate branch, never increment a count in the actual subtree here. Okay, so for M, I'm taking it as 1, and again Y as 1. Again, if I go for transaction T5, I'm having K, E, and O. Okay, so for K, E, O, I'll be going for the next branch. So, okay, so K value is 5. After K, I'm having again E. So again, the value is incremented to 4. Again, you can see KEO is already available. So instead of going for a new tree, I think just increment a count. So whenever you find the same pattern of transaction, increment the count by 1. If you are finding a new transaction, go for the subtree. This is how we generate your item set tree or FP tree. So because we have ended up with the transactions T5 now, this is the final tree. One second. Yeah, so I can say this is the final tree what I have obtained. Now, if you want to verify the tree whatever I have generated is correct or not, we need to check it with the values here. That is the support values. The value of K is 5. We have obtained K equal to 5. The support value is equal to 5, right? Yeah, here you can see, yeah, K is equal to 5, E is equal to 4, M is equal to 3, O is equal to 3, Y equal to 3. Let's check these values, right? K is equal to 5, we have obtained here. E is equal to 4, we have obtained. And M equal to 3, that is 2 plus 1, M equal to 3. And O is 3, and Y is also 3. So because I have verified that the values are matching with the actual support count, I can consider this as my frequent pattern tree. Okay, So this is how we construct a frequent pattern tree.